So, a very good evening to all the attendees and to my fellow panelists who have joined today to attend this special public lecture, which is going to be delivered by Professor J. Michael Kosterlitz, who's a Nobel Laureate Physics 2016. And he's a Harrison E. Farnsworth Professor of Physics at Brown University. And this special public lecture is being jointly organized by the National Academy of Sciences India Delhi chapter and the Science Foundation and Ministry of Education Institution Innovation Council, situated at Dayal Upadhyaya College, University of Delhi, under the aegis of the DBT Star College program. So before inviting Dr. Poonam to introduce Professor Michael, I would first like Professor Anurag Sharma, who is the chairperson of the NASI Delhi chapter, to say a few words about the chapter, its activities, its role in making the awareness of science amongst the young and the seniors. Over to you, sir.
Yeah. Good afternoon, good morning. Professor Kosterlitz, welcome to this lecture. I can't really say welcome to India or Delhi with virtual this thing. It is welcome to this lecture, and we are really pleased and grateful to you that you could find time to speak to our young students and many other scientists who, of course, have a lot of people are working in India in topological solid state materials or topological materials, and the phase transitions, two-dimensional materials, and so on. So I'm sure a lot of people would be interested in this subject. But of course, your title is very interesting. A random walk through physics to the Nobel Prize, and a lot of people would like to understand how it happens. that's the thing. Anyway, so welcome to this lecture, and we are looking forward to hearing your lecture. In the meantime, let me tell you also about this National Academy of Sciences in India that we have. In India, actually, we have 3 science academies, but this one is the oldest, established in 1930 by Professor Meghnad Saha, M.N. Saha, who was a well-known scientist who gave the ionization theory, which became very useful for astrophysics. This academy is located in Allahabad, or which is now called Prayagraj. It's on the banks of Yamuna. In fact, it is the place where Yamuna and Ganga and one more river, there's a confluence. So it's a very famous tri-junction of 3 rivers, and that is where it is situated. And it's apart from, of course, recognizing scientists through fellowships and so on, but it is also deeply engaged in promoting science among young children, school as well as college children, and a lot of activities are done by this. And in Delhi, we have a chapter of this particular academy, which is in short called NASI. It's a National Academy of Sciences in India, that is called NASI. And the chapter also, of course, has the same mandate, and we organize a lot of activities for college students, college teachers, and school children, senior school particularly, to promote science and science research and scientific thinking and scientific activities. And this lecture series, or this particular public lecture also, there are a lot of lectures which are going on these days. Manoj is organizing a number of lectures these days, the whole series, for months together. And so this lecture is also in the part of the same activity. And we also promote some research projects among college students. If they want to do a small project, we can fund that and so on. So in short, the chapter is involved a lot of activities in Delhi and around Delhi to promote science in general. So we look forward to your lecture in the same vein. I mean, we are looking at your lecture. Nobel Prize, of course, is a very big name, we all know, and a lot of people are interested in knowing how that comes and what kind of work is done. And so in that sense, it will be a great opportunity for our young students to listen to a Nobel laureate and understand and get inspired by it. Thank you very much for coming and joining. In fact, thank you very much for joining, and we look forward to your lecture. Thank you.
Thank you very much, Professor Anurag, for sharing your valuable thoughts about the activities which have been undertaken by the NASI Delhi chapter. Now, I request my fellow panelist, Dr. Poonam, to kindly introduce Professor Michael to the attendees.
Thank you, Manoj. A very warm welcome to all, and good evening according to Indian Standard Time, and good morning to you, sir. It's an honor and a pleasure for me to introduce you formally. Professor Kosterlitz earned D.Phil from the Oxford University as a postgraduate student of Brasenose College, Oxford. During his time at the University of Birmingham, he collaborated with David Thouless and a postdoctoral student at Cornell University. He was appointed to the faculty of the University of Birmingham in 1974, first as a lecturer and later as a reader. Since 1982, he has been professor of physics at Brown University. Kosterlitz does research in condensed matter theory, 1- and 2-dimensional physics, in phase transitions, random systems, electron localization, and spin classes, and in critical dynamics, melting and freezing. He has been awarded the Maxwell Medal from the British Institute of Physics and the Lars Onsager Prize from the American Physical Society, both for his work on the Kosterlitz-Thouless transition. He was also awarded the Nobel Prize in Physics in 2016, shared with David Thouless and Duncan Haldane for work on the Kosterlitz-Thouless transition. Welcome you, sir, and over to you. Thank you.
Thank you very much, Poonam. I request Professor Michael to share his screen and deliver his talk.
I thought. Am I sharing the screen?
Not as of now, sir. You have to click on the share screen option. Yeah, it's coming up. Yeah, it's there.
Okay, good.
Yeah.
I'm not very good at this.
No problem, sir. It's perfectly fine now. Yeah, sure.
Okay, I should start, yes?
Yes.
Okay. Now, I'm very pleased and honored to present this lecture, which is, you see, this title slide is entitled Topological Defects in Phase Transition in 2 dimensions, but there's a subtitle called A Random Walk Through Physics to the Nobel Prize. And I will talk about the subtitle in this talk. The reason why I'm using the same slide for both titles is because I find that making up PowerPoint slides is a bit beyond my abilities. And so I'd rather make up one slide for 2 things rather than 2 slides, one slide for each individual talk. So let me start. So if I can find my cursor, here we go. Just to, in 2016, I happened to be on sabbatical leave in Finland. It was sort of and we were in the car park, underground car park, just waiting to go up to the mall for sushi and beer for lunch. And my cell phone went off my pocket. So I answered it, and this Swedish accent came over the phone saying, blah, 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 Nobel Prize. And, when I heard this, I really couldn't believe it because it had been more than 40 years since I'd done the work. And so basically I'd forgotten, all about it. I had no idea that it was even being considered for a prize. And so I was very shocked, but very pleased to hear that I got a Nobel Prize. Now, let me say, I can hardly recommend winning Nobel Prize to anybody because the Nobel Prize really involves the most fantastic week in Stockholm, which is, they had the most amazing week, and it was absolutely wonderful. We had a wonderful time. Sorry, my eyesight is absolutely terrible. Here we go. Nope, going the wrong way. Okay, just to basically as extra piece of proof that we were actually there. This is a photograph which every Nobel laureate is presented with. It's my wife and myself there in the middle, flanked by the King of Sweden and the Queen of Sweden, and then the other characters are the Crown Princess, and so on and so forth, and their husbands. So this is just proof that we were actually in Stockholm meeting the Swedish royal family. Now, I thought I'd start by, basically telling you a bit about my life and how so this is all part of my the random walk bit. So this is a picture of my father and myself at a rather young age outside our stone house in a little village in northeast Scotland called Cults, which is just outside the city of Aberdeen. Now, I was actually born in Aberdeen back in 1943. Not that I remember that event, but apparently it happened. Now, my parents were actually German. My father came from a non-practicing Jewish family, and my mother came from a right-wing Aryan family. So, as you might understand, my background is a little bit weird because it's quite unusual for a Jewish man to marry a right-wing Christian woman in Germany, particularly back in the 1930s. Now, my father worked at the big hospital called the Charité in Berlin, and in 1932, Hitler came to power, and Hitler permitted him to continue working, but as a Jew, he couldn't be paid. So at this point, my father decided that things were not good in Germany, so he used his contacts outside Germany and managed to land a few temporary job offers in several places. But Aberdeen University offered him a permanent position, which he accepted. Now, of course, there were two reasons why Aberdeen was very attractive. Now, remember, at the time, Aberdeen University wasn't very well known at all. It was a very minor university, an old one, but very minor, in a rather cold, windy city in the northeast of Scotland. Now, of course, there were two reasons why Aberdeen was very attractive. The first one was, of course, the security of a permanent position, because under the circumstances, my father being a refugee from Hitler, security became a sort of dominant consideration. Of course, there was another reason why Aberdeen happened to be quite attractive, because there was a Nobel laureate called MacLeod who worked there, and my father wanted to collaborate with him. But unfortunately, MacLeod had the bad grace to drop dead shortly after my father's arrival. And so he had to make his own way on his own. Now, he actually worked in Aberdeen for about 60 years, finally quitting at about age 90 when old age took over. Now, my mother followed my father from Germany to Scotland. You see, they weren't allowed to get married in Germany at the time because of my father's Jewish background. And so they got married in Glasgow in Scotland in 1934, settled into a small house in a small village called Cults, about 4 miles from the centre of Aberdeen, and that's where I grew up. Now, I went to school in Aberdeen, a semi-private boys' school, Robert Gordon's College, where I got a very good education. The main good thing about the education was that I could actually quit the subjects I disliked when I was 16 and concentrate on the things that I liked, or rather the ones I was good at. My parents never overtly tried to influence my choice of study, and I naturally gravitated towards maths and science. I disliked all the humanities, literature, languages, fine arts, etc., etc. Now, I think this is because of my very poor memory. You see, I like to say that I can remember a maximum of 10 facts, but I'm not too sure about the last 4. And so I have to make do with 6 facts of which I'm fairly certain. Now, all the humanities subjects are very memory intensive: languages, history, geography, literature, and so on and so forth. And I always struggled with those. And also, it seemed that in those subjects, one's own opinion of what's going on doesn't seem to matter as much as the instructor's opinion. And I've never been able to understand why my own opinions about a piece of literature or something was any less valid than the instructor's opinion. But that's all a matter of taste and opinion. However, mathematics and the sciences, on the other hand, could be handled with a minimum of memory and an extensive use of logical deduction, which suited my way of thinking. Now, my education was a bit torturous. As I mentioned, I went to school from age 4 to 16 at this school, Robert Gordon's College in Aberdeen. And then my father decided that I might be good enough for a very good university, for Cambridge, in fact. So I was sent to a school in Edinburgh, which is a couple, 120 or so miles south of Aberdeen, because at Edinburgh Academy, the teaching went up to the English advanced, A and S level, which at the time was required for the best English, to get into the best English universities. Now, I got through this quite easily, getting top grades, although mind you, I didn't particularly enjoy my 2 years on my own at school in Edinburgh. But I won a scholarship to Cambridge to study the natural sciences. And the nice thing about this was that this degree did not include any other subjects. Initially, I got a bit bored with the teaching because I'd learned almost all of it at my Edinburgh school. However, the chemistry was fun because, as you all will understand, to a somewhat mischievous kid, it's possible to do all sorts of illegal experiments. At least at that time, it was possible. Of course, these days the regulations are such that chemicals like I could play with were simply, you're not allowed to use them these days. But of course, I got turned off by an incident in the chemistry lab where a test tube of some colorless liquid I was staring at suddenly started to change color. So I thought, oops, this doesn't look good. So I held it out at arm's length to the side just in case, and then it exploded and sent shards of glass into my cheek and so on. To this day, I've got no idea what happened. There were 1 or 2 other incidents during which I discovered that I am, in fact, red-green blind, which makes distinguishing test tubes of different shades of reddish liquid somewhat difficult and sometimes dangerous. And of course, as an aside, as you will can well imagine, it makes distant traffic lights a little bit tricky. You see, to me, red is not a loud, if you like, color. It's a color that to me it's a muted color that blends well into the background. For example, I've always had terrible difficulty finding wild strawberries, these tiny little red berries, which, as far as I was concerned, hid themselves among the green leaves. And it wasn't until I was quite well in my 20s that I discovered I was actually colorblind. That explained, red-green blind. That explained a lot of my problems in choosing clothes and so on. Occasionally, I ended up with the most disastrous choices of clothing because I simply couldn't see that the coloring was atrocious. Now, all these problems, together with my poor memory, made me decide to go for the simpler but safer subject of physics. Chemistry to me seemed a bit dangerous because if liquids sort of exploded without any warning, I thought that physics was, a somewhat safer subject. But my academic Cambridge career also got disrupted when I joined the Cambridge University Climbing Club. You see, this was a club that ran a bus every weekend to the cliffs, either in Derbyshire, a couple of 150 miles north, or to North Wales or the Lake District. And I was introduced to the sport of rock climbing and found that I was actually quite good at it, and very quickly became completely addicted to it. You see, there's nothing to compare with the rush one gets when you step out into the unknown, high up on a steep cliff, knowing that a mistake could have serious consequences. And these consequences are up to and including death. And it's amazing how this concentrates the mind. And it also becomes very addictive. And so the climbing became my main interest. So my three interests when I was at university were, number one was definitely the rock climbing. Number two was physics. And probably an equal passion was my newly acquired Swedish girlfriend. Now, with all these distractions, it wasn't surprising that I didn't do as well as expected in the final examinations. So I persuaded my father to finance an extra year at Cambridge to try to rescue my academic career. And so I did what is called in Cambridge Part 3 mathematics, or applied maths. But my climbing passion intervened yet again, and I didn't perform as well as I had hoped and other people had hoped. So I was turned down for graduate school in high energy theory at the Department of Mathematical and Theoretical Physics in Cambridge. Ironically, I was offered a place as a graduate student in Cambridge by Sir Neville Mott to study solid state physics, because this is the field for which I would later win the Nobel, much later, would win the Nobel Prize. However, I turned this down in favor of graduate school in Oxford in high energy physics, which of course at the time was the glamour subject. Now in Oxford, I worked on what are called dual resonance models, otherwise called the Veneziana model, which were precursors to modern string theory, of which some of you may have heard, and published a couple of papers with other graduate students. And at the time, these were probably never read. On completion of my D.Phil, which is what a PhD is called in Oxford, I was awarded a 2-year fellowship from the Royal Society, which could be used anywhere in Europe, as was my closest friend in Oxford. So in 1969, or late 1969, my girlfriend Berit, who's now my wife of more than 50 years, and the other Oxford graduate student went to Torino, University of Torino in Italy. Now, I chose to go there for two reasons. The main reason was the proximity to the mountains, but also the physics was supposed to be quite good, because there were two people there who were quite well known, called, one was Tullio Reggi of Reggi Poles, and the other one was Sergio Fubini. Now the three of us, that's my fellow graduate student, my girlfriend, who's now my wife, rented and shared an apartment, and of course this made the ladies in the local milk shop very curious, because they could never figure out the relationship between the three of us. I mean, they knew that there were these three foreign students renting an apartment nearby, but they could never quite figure out what the relationship between us was. But remember, this was 1969, which is a long time ago, and the morals were completely different then to what they are now. But in any event, I had a wonderful year in Torino, because my scholarship from the Royal Society was sufficiently generous, I beg your pardon, that Berit and I could eat well and go skiing in Italy, France, and Switzerland every weekend, and for the occasional week in the winter. Of course, it's not cheap going for a week skiing in Europe, but I had climbing friends who rented apartments in various ski resorts, such as Verbier and Lausanne in Switzerland. And so Bert and I could always sleep on a floor for a night or two, and so we rarely had to pay for hotels. So we could ski basically all over Europe for that winter. It was a great winter. I also managed to continue with my rock climbing, and actually did some climbs which were not in Italy, which weren't repeated for several years. I was introduced to young mountaineers from Fiat, the car factory. The T in Fiat actually stands for Torino, the city. Now, this was a fun experience because they were very good climbers, but did not speak or understand a word of English. And communication is vital when, each one depends on one's climbing partner, when you're hanging on a steep cliff, sharing one rope. And needless to say, my Italian improved dramatically, as you might understand, because I came very motivated to learn it. In fact, I think in 2018, I returned to Torino in February 2018 to receive an honorary doctorate in physics, and discovered that in that region of Italy, I'm better known as a climber than as a Nobel laureate. In effect, I'm labeled as introducing, and I quote, the new morning of Italian climbing, the Nuovo Mattino. Now, let me tell you a story. When the winter of skiing was over, I needed to go climbing with my newfound climbing partners. Sorry, I'm missing the slides. Now let me, there's some of my climbing partners. There's me in the background, and the two other very good English climbers in the foreground. In the center of this picture is a climber called Mick Burke, who unfortunately died on Everest. I think it was 1975, and that was a very unfortunate occasion. But anyway, to continue my story, with my newfound Italian climbing partners, I was in a car, I think it was my car, driving along a very narrow road up the Val d'Orco in northern Italy. And I thought I'd entered paradise, because on both sides of the valley, there were, square kilometers of unclimbed rock. Now, you must remember that I came from Britain, where cliff climbing was a well-developed sport, and almost every square foot of rock had been climbed on. So finding some new unclimbed rock was quite, it was the most amazing gift. And it's in Britain, any unclimbed cliff that people discovered was kept a carefully guarded secret until the discoverer had basically climbed every root in the cliff that he or she could manage. And to find such an expanse of virgin rock was really unheard of. Now I'll come to this in a moment. Now, as we drove up the valley, we passed a 20-foot, 6 or 7 meter high boulder with a thin crack splitting one of its gently overhanging sides. And when I saw this, I shouted in Italian, "Stop the car," jumped out, put on my climbing shoes, and managed to get up the crack. The boulder is actually that rock on the right of the screen, and you can see the thin crack splitting, sort of towards the left-hand side of the face you can see. I managed to get up this crack, which is now, believe it or not, called the Fessura Kosterlitz. Now, I didn't find it terribly difficult, but my climbing partners couldn't repeat this. And as a matter of fact, it took 10 years before this little 20-foot high crack was actually repeated. But now, of course, this rock has been climbed hundreds of times. There's somebody going up the little crack. But it's interesting because this boulder has become an important feature of the little village of Cerasoli, which is within a couple of kilometers of further up the valley. See, at one time, the road was straightened. Let me go back for a minute, you see, and there was a tunnel built. This structure on the left-hand side there is this tunnel under construction. And this rock was supposed to be blown up. But the climbing community, the Italian climbing community, thought otherwise and wanted the rock to be preserved. And so they made an enormous noise, and so the rock stayed and the road was diverted around it. And in fact, back in 2018, in February, I was invited by the mayor of Cerasoli and the regional climbing community for a get-together in the village. And I was feasted and made an honorary citizen of the village. I was also told, to my surprise, that because of me and my rock, the tourism of the village had been booming ever since, because climbers come from all over the world to try their luck at the crack, and I was thanked for that. And in fact, at the time, it felt like getting a Nobel Prize again, but this time for rock climbing. Now back to my path, through my random walk through physics. You remember that the visit to Torino, my year in Torino, was an accident, because I got this fellowship with a bit of money, and I could take it anywhere I wanted to take it. And so I chose Torino University, mostly because it was close to the mountains. And so I could indulge my addiction to rock climbing. So my fellow postdoc and I wrote a single paper on a topic called the vertex function and dual resonance models. Otherwise, these days it's called string theory, which apparently is still quoted in the literature. Now, the obvious place to go after CERN, after Torino, was CERN in Geneva, for two reasons. First, because Geneva is very close to the mountains, and I would be able to continue to indulge my passion for rock climbing, but also the physics is very good. And remember, at the time, I was a high energy physicist. Now, so both my colleague and I sent in applications to CERN. He was accepted, but in my usual disorganized fashion, my application was late. And I got the reply, sorry, all the desk space is gone. Please apply again next year. So I now face unemployment. And my girlfriend, Berit, just looked at me and, muttering some very uncomplimentary epithets, walked down to the railway station in Torino to buy an English newspaper, which had academic job advertisements. She came back to the apartment, sat me down at the kitchen table, put the advertisements in front of me, and said, apply. So under the circumstances, I didn't have much choice, and I found 3 positions, and I was offered all 3 positions and accepted a 3-year postdoc position at the Department of Mathematical Physics at Birmingham University, and very reluctantly signed the contract. Shortly afterwards, I got a letter from CERN saying that they had decided that they would have 2 people per office instead of 1, so I could go after all. And I immediately said to my girlfriend that I would renege on my Birmingham contract and go to CERN to have fun in the mountains. However, both my father and my girlfriend were very much against this idea, because they argued that, or were of the opinion that, having signed a contract, I was obliged to go to honor it and go to Birmingham. Now, Birmingham was the last place I wanted to go to, because Birmingham was was a large industrial city in the middle of England with no mountains in sight, and was the last place in the world that I wanted to be at. But as it turned out, Birmingham was quite a nice city to live, just after all, despite the terrible unemployment, because that was the time when all the car factories were going out of business. And so the unemployment was pretty bad. I think it was about, in Birmingham when we were there, it was about 20% or something like that. However, the university was quite good. The Cadbury Estate, as an area of Birmingham, was a lovely place to bring up a family, and we made several friends. The Lickey Hills was our favorite family outing spot. So my first real job was in the Department of Mathematical Physics at Birmingham University, first as a research fellow, then a lecturer, senior lecturer, and finally as a reader. Now, in hindsight, it turns out that professionally, Birmingham University was the best choice I could have made. Although, of course, at the time, that was hard to believe. In the first year or two, I continued doing the long, tedious calculations in high energy physics. And I was on track with writing up my results several times, but was repeatedly thwarted by a group at Berkeley who were doing exactly the same thing, and they published first. Now, as I mentioned earlier, I was actually quite good at rock climbing. So I started to consider very seriously giving up physics to become a professional mountaineer. Now, fortunately, Berit, then my girlfriend, now my wife, 52 years, vetoed this idea. Now, as an aside, a few years later, I came down with a an unfortunate neurological condition called multiple sclerosis, which affected my balance and destroyed any climbing ambitions I might have had. I had to make do with my day job as a physicist and teacher, which does not need the same athletic ability as rock climbing. Now, back to my story. I was very upset with the Berkeley group and descended on my colleagues, asking if they might have a problem that I might try to solve. Now, I went from office to office, pitching my sob story, and the answer was, sorry, no, I don't have a problem. Eventually, I found myself in David Thouless' office, listening to him talk about a class of problems in 2 dimensions. Now, he talked about things, some physics that I had no idea about. Talking about vortices in superfluid helium, superfluid flow, superconductivity. And I think the word topology also appeared somewhere. I found his ideas very difficult and very challenging, but they slowly started to make sense. In fact, Birmingham was the place where I learned what physics is really all about, working with one of the great minds in physics, David Thouless. And together, we managed to solve one of the main puzzles in phase transition in 2 dimensions, for which I later got my Nobel Prize. I realized then that physics is something I could actually devote my life to. And we discussed the problems further and wrote up a couple of papers which solved the long-standing problem of phase transitions in 2 dimensions. For those of you who don't know what that problem is or was, it was a combination of 2 things. The first thing was there was a rigorous theorem which said that which basically stated that there was no long-range order at any non-zero temperature in 2-dimensional systems with short-range interactions and continuous symmetry. And this is very relevant to situations like superfluidity in thin films of helium-4. Then, of course, was also the rules of phase transitions set forth by the Russian physicists, particularly Lev Landau, who said that the difference between a low temperature ordered phase and the high temperature disordered phase is that in the low temperature ordered phase, there was long range order, and the high temperature disordered phase, there was no long range order. I mean, this is just like, see, take a 2-dimensional magnet, or a magnet in any dimension. And you know that at high temperatures, little magnetic moments sort of point in random directions due to thermal fluctuations. So the average magnetization in this system is 0. Then at low temperatures, these little atomic or molecular magnets tend to line up so that there's giving you a macroscopic magnetization, and that's called long-range order. And therefore, in 3 dimensions or higher, there is the low temperature phase has long-range order, and the high temperature phase does not. So this was the rule of Lev Landau, that a low temperature phase had to have long-range order. However, now remember, go back to the mathematical theorem, which said there's no long-range order in this class of two-dimensional systems. So therefore, the theoretical conclusion one would have to come to is that there is no phase transitions in such systems. So this is one of the papers that Thouless threw at me, and this is a paper by Chester, Yang, and Stevens, published back in 1972. And what it shows is the results of a clever experiment. And this experiment involved, you take a crystal, and of course, if you have a crystal and you put it on a torsional oscillator, it will have a certain resonant frequency. And this resonant frequency will depend on the mass of the oscillating crystal. And the heavier the crystal, the more mass the crystal has, the lower the resonant frequency. So what Chester and company did was he absorbed a thin layer of helium-4 on the surface of the crystal. And they measured the frequency of the oscillations of this crystal with the helium absorbed on it. Now, when you absorb a very thin layer of stuff onto the surface of a crystal, maybe 2, 3 atomic layers thick, one would expect naively that all the atoms of this helium absorbed in the crystal will simply stick to the crystal. And when the crystal oscillates, the helium atoms will move with the crystal, therefore increasing the mass of the resonant body, and therefore the resonant frequency would decrease because the mass is increased. And so this is a graph of the reduction in the resonant frequency against on the horizontal axis, the coverage of helium on the crystal, just basically amount of helium absorbed on the crystal. And so it's arranged, this graph is arranged in such a way that if every atom of helium is stuck to the crystal, then the resonant frequency, the decrease in the resonant frequency, would follow this solid straight line. And the little circles are the experimental data. And we see that for low coverages, the experimental points agree with the theoretical curve and follow it for a while as the pressure of the gas, which is in equilibrium with the crystal, is increased. In other words, more gas is absorbed onto the crystal. And we see that the experimental points agree with theory for a while. But then when the coverage reaches a certain point, if you like, when the film gets thick enough, suddenly the experimental points break away from what's expected theoretically. And so the difference between the straight solid line and the experimental points is a measure of the amount of helium, the amount of absorbed helium that has decoupled from the crystal. So the situation is, what you have here is that the crystal is vibrating, and some fraction of the helium absorbed in the crystal simply does not vibrate with the crystal, decouples from the crystal, and therefore the mass of the resonating body is not what you think it is. It's smaller, and therefore and is decoupled from the crystal. And the most obvious interpretation of this is that part of this helium film has become superfluid, because as you well know, or you should know, a superfluid doesn't couple to the substrate. And so therefore what's happening here is the crystal is vibrating and some of the fluid is simply not responding to this. And therefore you'd have to, the obvious interpretation is that this system has undergone a phase transition from a normal fluid to a superfluid. Now, let me go to the next slide. So what we did, or at least, what David and I did, the problem that David proposed to me was to understand this. And eventually, after reading some papers, in particular, a paper written by Phil Anderson and his student Gideon Yuval, and this paper was written in the very early 1970s, 71 or something like that, where they looked at a problem basically boiled down to a one-dimensional Ising chain with interactions between spins which fell off like 1 over the separation squared, one over r squared interaction. And their solution to this problem was actually done by a method which these days would be called the renormalization group. Anderson and Yuval called it poor man's scaling. They didn't call it renormalization group, but this paper by Anderson and Yuval preceded Wilson's paper. So in my opinion, I think that the originators of the renormalization group for critical phenomena were really Phil Anderson and Gideon Yuval, and although Ken Wilson's technique was applicable to a wide range of systems, whereas the technique of Anderson Yuval was limited to very special systems. Now, of course, Thouless and I were completely, got quite excited about this paper by Anderson Yuval, because the essential excitations in this system were domain walls between regions of up spins and down spins. And these domain walls interacted with each other. They interacted with each other logarithmically. In other words, the interaction between two domain walls was proportional to the logarithm of the separation. And so if one assumed that these domain walls were very dilute, in other words, very few of them, one could treat the system as an expansion, but in what is called the fugacity of the domain walls, which you could assume the fugacity, which I call Y on this. Because this pair of equations in the top right corner of that diagram are the renormalization group equations, and all the physics is reduced to these two simple equations. And the thing is that if you plot, this L measures this clever trick, because what you do is you say that, okay, the initial cutoff distance is, say, the lattice spacing, and then you increase this lattice spacing by a factor e to the L, and integrate out all the excitations which happen, on short distances. And you can, and so the conclusion is you end up with the same problem you started with, but with different interaction parameters. And so, yeah, as I said, so Thouless and I thought, well, maybe we can apply the techniques of Anders and Yuval to the problem of the transition in a helium film, because after all, the difference between a superfluid phase and a normal fluid phase is that there is no dissipation in the superfluid. The fluid can flow without any dissipation in the superfluid, but in the normal fluid, there is dissipation in the flow. And so the idea was to start with a theory of a superfluid, and then ask the question, how is the flow dissipated? What do you add in to dissipate the flow? Well, in a superfluid, the only thing that can dissipate the superfluid flow are so-called vortices, because what happens is, in a superfluid flow, if you have a vortex pair of equal but opposite vorticity, and you simply, that there will be vortex pairs generated by thermal fluctuations, because a vortex pair has got relatively low energy. And then you could imagine that this vortex pair can drift further and further apart, and eventually unbind, become free, and go right around the system and annihilate each other at the back of the system. Now, or at the sides of the system, edges of the system. Now, what this will do, this process will reduce the superfluid velocity by some small amount. But if there are free vortices present, this process can happen over and over and over again. And so the superfluid flow will decay. And if the system does this, you have to say that this is actually a normal fluid. And so what we actually did was we managed to cook up a theory of a set of interacting vortices in 2 dimensions. And we constructed these so-called renormalization group equations, which are in that, so simple looking equations, which describe how the essential parameters of the system, this K, which is basically is proportional to 1 over temperature, and K is the interaction constant between 2 vortices which interact logarithmically with a separation, and this parameter Y is the fugacity. Because it's basically just the exponential of minus the energy of a vortex core. If you have to have a core, because if you think of a vortex is just like water running down. If you pull the plug out of your bath and you watch the water draining away, it swirls round and round in circles as it drains out, and that's a vortex. And these vortices in a superfluid are basically the same sort of thing, except the center of the vortex must be a normal fluid, because the velocity of the flow, you know, if you take the a continuous system, and the velocity must go to infinity at the center of the vortex. But if you look at the theory of a superfluid, if the velocity of the flow gets too large, the system has to become normal. And so one can say that there's a little blob of normal fluid at the center of the vortex, and the normal fluid has got higher energy or higher free energy than the superfluid. And so that allows you to parameterize the probability of having, of a vortex being present as proportional to the exponential minus the energy of a vortex divided by kT. So that's basically what this fugacity y is. Now, you'll notice from this little diagram that these little arrows are the direction of increasing L. So the bottom right-hand corner of this picture is for large K, large interactions or equivalently very low temperatures. And we notice that as we do this rescaling game, this fugacity y tends to 0, because you start with a system with some physical value of K and Y. And as you do this coarse graining, you get a new K and a new Y. And for some range of the parameters, the physical parameters, as you increase L, Y gets smaller and smaller, and eventually it goes to 0. Now, when this fugacity is 0, this means that there are no vortices, because the effective energy of the core has become infinite. Therefore, the probability of a vortex is 0. So there are no vortices. And so if you've got no vortices, there's no way of dissipating the superfluid flow. Therefore, you'd have to say that if the fugacity flows to 0, this means that your initial system is a superfluid. And then, of course, if there is a special situation where the flow follows a straight line down to 0 fugacity, and if you start with a system lying above this straight line, you notice the flow follows the straight line to start with, and then eventually turns round, and then the effective fugacity starts increasing. And a system that does this has to be interpreted as being actually a normal system, a system of normal fluid. And so this is actually describing, this diagram actually describes the phase transition. Now, let me see what happens if I go to the next slide. Oh, sorry, I'm going the wrong way. Okay, now, the crucial predictions of our theory are the following. First of all, the first quantity is what is called the measured stiffness, or the renormalized stiffness. And this is, the renormalized stiffness is a measured quantity. It's in principle measurable. And this will depend on the initial physical parameters, which I call K0 and Y0. We're assuming that we can parameterize the system in terms of these two parameters, this effective interaction constant K and its effective vortex fugacity Y. And in 2 dimensions, it happens that as we change the microscopic cutoff, or we increase L, that this so-called stiffness constant is then a function of the new K of L and Y of L, but it doesn't change its value. In other words, now this is rather important, because you see the stiffness constant, this K, is actually contains what is called the superfluid density, which is a quantity which with dimensions of mass per unit area. And so it turns out this stiffness constant is basically the normalized superfluid density, or the measured superfluid density, if experiment can actually measure it, divided by temperature times a bunch of fundamental constants like Planck's constants, the mass of the helium atom, and Boltzmann's constant. And so this stiffness constant, this K superscript R, is actually proportional to the measurable superfluid density. And of course, the superfluid density will distinguish between a superfluid and a normal fluid. And what our renormalization group tells us, that this is equal to the same renormalized stiffness constant as a function of the effective interaction parameter and the effective fugacity at when we scaled to infinity. But if you're below the critical temperature, you'll remember that as we scale this cutoff to, that this Y scales to 0. So if we're below the critical temperature, this is equal to this renormalized stiffness constant calculated for a system with no vortices. And so this is just the value of this interaction parameter, K of infinity. And this quantity, you can work it out, is just 2/pi plus a constant times the square root of the deviation from the critical temperature. Therefore, one has if we go to a temperature just below the critical temperature, called Tc minus, then the measured superfluid density, superfluid mass per unit area, at just below the critical temperature, divided by the critical temperature itself, is given by this combination of fundamental parameters, like Boltzmann's constants, the mass of the helium atom, and Planck's constant, and 2/pi. And this works out to be 3.49 times 10 to the minus 9. I'm sorry, that's a misprint that I have to correct sometime. Grams per square centimeter per degree Kelvin. Now, this prediction is, within our theory, is inescapable. No matter how you fiddle about with various parameters, you cannot change this prediction. So this prediction is actually a smoking gun prediction, which, it measures, it's in principle, an experimentally measurable quantity. And if this experimentally measurable quantity turns out to have a different value to this prediction, then the theory is wrong. So let's have a look to see what actually predictions are. And this is a slide of some experimental work. The slide is taken from a paper in Physics of Lattice in 1978 of David Bishop and John Reppy at Cornell, who did a set of experiments. And it's a summary of their results plus several other experiments were done on the same system, third sound experiments by Hallock, Muschel, and Rudnick. And the experimental points, so we have, what we have here is the vertical axis is the superfluid density just below the onset temperature versus the onset temperature. And of course, you can change this onset temperature easily, because if you just make your helium film increase its thickness a bit, you'll make the critical temperature bigger. So the critical temperature can be varied quite easily. And so if you plot these points of the superfluid density versus just below the critical temperature against the critical temperature, you find this cluster of, the points seem to follow a straight line. Now, if you simply take a best fit straight line through this, that is basically that solid line. But then somebody informed the authors that, look, these characters from England, Kosterlitz-Thouless, they have a theory, and they predict the slope of the straight line. And our prediction for that slope is, it's this particular, remember, I told you what that value was, 3.5 times 10 to the minus 9 grams per square centimeter per degree Kelvin. And so if you plot the straight line for our prediction, it goes straight through the cluster of experimental points. Now, this is viewed as confirmation of the theory, because remember I said that this prediction is inescapable from the theory, and so that it just so happens to agree quite well with experiment, and so it's viewed as confirmation of the theory. Okay, now, so you can say that for superfluid helium films, the theory is pretty much confirmed. Now there's another system to which one can apply the same sort of theory, and this is the melting of a two-dimensional solid. Okay, now in a two-dimensional solid, again, there is no long-range crystalline order, because the Merman-Wagner theorem, this rigorous theorem, says there's no long-range order in 2 dimensions. Therefore, there's no long-range crystalline order. But there's still the possibility of there being a finite elastic constants below some melting temperature. And so one can cook up a theory which is basically identical to the theory of vortices in a superfluid. And these so-called topological defects are defects which can reduce the elastic constants. And these are well known from engineering and so on. They're called dislocations. And in 2 dimensions, they are point defects, because the dislocation is a well-defined core. And then you have the elastic, the effects of the dislocation spreading out from the core. And one can apply the same sort of theory, the statistical mechanics of a set of interacting dislocations, And you can ask the question, you can parameterize these dislocations in terms of some interaction constants and a fugacity, just like for superfluid helium, and then see if you can cook up some renormalization group approach, some scaling approach. And if the dislocation fugacity increases as you change the cutoff, that means that there is there is a large probability of dislocations being present in thermal equilibrium. And if so, if there are a large number of large concentration of dislocations, the system will have zero shear modulus. In other words, the system will not be able to resist a shear stress. Now, any system that where the shear modulus vanishes, it's not a solid, it's a fluid, because that's the very definition of a fluid. It's got a vanishing shear modulus. And so, well, as I said, one can cook up a similar theory to that theory for superfluid helium. And this theory for solids is based on the theory of, the statistical mechanics of a set of interacting dislocations. It's more complicated than the theory of vortices, but it's in spirit, it's the same. And so there are basically the same sort of predictions come out of this theory as came out of the theory for two-dimensional superfluid. And this theory gives you the prediction that at low temperatures, basically there are no dislocations. But as you increase the temperature, the renormalized Young's modulus suddenly scales to zero, or at least scales to some particular value, which happens to be about 50. This combination of of elastic constants called Young's modulus scales to the value 16 pi, which is about 50 at the melting temperature. And so the theoretical prediction is this red line, which eventually scales to this special value of, of 16 pi. The experimental points, this was done, it took a number of years for the experiments to be done, because the experiments are not easy, as you can imagine. And they're actually done by absorbing or simply putting a set of polystyrene spheres, tiny little polystyrene spheres, trapping them at a liquid water interface, at a water air interface of a drop of water. And these polystyrene spheres were actually heavier than water. And so if you take an inverted droplet, these spheres will get trapped at the interface of the inverted droplet. And then the positions of the particles can be measured by a CCD camera and analyzed, the data analyzed at one's leisure. And so the experimental points are these points with these rather large error bars. But at least they're consistent with the theoretical prediction. Now, the bottom right of this picture is another set of experiments we've done earlier. They were done, these experiments are done with electrons absorbed on the surface of superfluid helium. And there are, one can make similar comparisons between the theoretical data, the experimental data, and the theory, and that is the comparison is given in the bottom right-hand corner. The other points without error bars are the results of a computer simulation, a Monte Carlo simulation. The normalization group predictions are now, it's been shortened to the KTHNY theory, standing for Kosterlitz-Thouless, Halperin, Nelson, Young. You know, several people worked on the theory of two-dimensional melting. I personally had really wanted to work on this, but that was the period when I got my, you know, had my first attack of multiple sclerosis, which basically knocked me out for several months. So I was basically unable to work during that time. So unfortunately, I wasn't directly involved in this theory. It's the reason why Kosterlitz and Thouless get their initials onto this is because the theory used by Halperin, Nelson, and Young is based very closely on the theory developed by David Thouless and myself for the two-dimensional superfluid helium films. And so, but to come back to the melting experiments, we see that the comparison between theory and experiment is quite good. And this prediction that the Young's modulus just below TC divided by TC is this universal constant of 16 pi, although it's not measured that brilliantly because of the difficulty of experiments, it's basically very consistent with experimental measurements. And so now there's another system where where the same sort of theory applies and has certain predictions. And this is basically some experiments on cold atoms. And the agreement, again, between theory and experiment is quite good for this system as well. Oops. I seem to have lost my acknowledgement slide. So let me just say that I would like to thank my collaborators, and I hope that you learn something about my random walk through physics from, through Cambridge, Oxford, Torino, Birmingham. The jump between Torino and Birmingham was at the time for me a complete disaster, because it suddenly meant that I had to leave the mountains and go to the flat middle, a big industrial city in the flat middle of England, and work there, because I really wanted to go to CERN in Geneva. But since I was so chaotic in my applications, I couldn't go there and had to go to Britain, back to England. But if I hadn't gone to Birmingham, I would not have met David Thouless again and worked with him. and I would not have done the work which won me the Nobel Prize. And so these accidental movements from one place to another, like, first of all, going to Torino, then going from Torino to Birmingham. And if I hadn't ended up in Birmingham, I would not have done the prize-winning work. So that is, and if you don't call that a random walk through physics, I don't know what is. And so that is basically the end of my talk. And I must, of course, thank my wife very much and my children, who had to put up with a really strange father with his strange hang-ups and pursuits. And so basically, my younger life was very rewarding, and I'm very grateful to have been able to work on a fascinating problem of, involving some very new physics, which involved, things like topology and so on. And so it gave me an opportunity to work on this subject. And it was my first problem in condensed matter physics. And it's amazing that the first project I ever got in condensed matter physics, which I went to because of, basically I failed at doing high energy physics, actually won me a Nobel Prize, or at least a quarter share of the Nobel Prize. And that is really all I have to say. And I hope that you learned something from this talk, and that no matter how dark your path through life seems to be, there's always hope that things will work out. Although you never know how it's going to work out. And so I hope you take the lesson from my own experience, and just don't give up. So thank you very much for your attention.
Sure. Thank you. Thank you very much, Sop, for your wonderful lecture and enlightening us about the various aspects of the topological systems in the two-dimensional systems, and also covering up quite in detail about their journey, or I'll say your random walk towards your Nobel Prize. So before asking Professor Anurag Sharma to say a few words, I have two questions which have been posted by the attendees. So I need your permission to put up those questions. So the first one is, can you please explain how to determine the phase transition in Coulomb crystals, which is there in a linear ion trap? Shall I repeat the question, sir?
No, I understand what you're talking about. Okay, the first thing about an ion trap is that, to be able to measure, make a good experimental measurement of a phase transition, you really have to be careful that your system is large enough so that what you're seeing is not just some short distance effect, but that it's really the characteristic behavior of a large system. Because remember what the phase transition gods have told you, that strictly speaking, there is no true phase transition, at least a continuous phase transition, a second order phase transition in a finite system. You basically have to have a mathematically, you have to take the thermodynamic limit, which means an infinite size system. And of course, experimentally, all this means is that it should be a reasonable size system, not too small. And of course, I always question the problems in an ion trap, whether your system you're talking about is actually large enough to apply any of the theory to, simply because you don't have that many atoms in a trap. And so the only way really of analyzing your data is eventually to do compare it with some finite size scaling predictions. Because if you have a system that is, quote, large enough, then you can show that this will, as you change the system size, you ought to have certain scaling laws apply. And the only real way of deciding if this small system is actually aping a phase transition is to compare it with the finite size scaling predictions. And if that comparison is good, then you can say that if I could make a big enough system, I would see a true phase transition. This is a problem in principle of these ion traps, is that the systems are just too damn small to be able to really say you're seeing a phase transition. I mean, I'm not saying you don't. You probably do see a phase transition, and what you're seeing is probably real. But if you're being picky about it, and you really want to, dot all the I's and cross all the T's, then you really ought to do, some finite size scaling by looking at systems with different numbers of atoms in the trap, and comparing the properties of these different size systems with certain predicted scaling laws. And of course, this is an incredibly difficult business. I don't much want to say about that, because.
Okay, sir. So I'll take up the last question in that case. One of the attendees asked that the topological defects in curved two-dimensional crystal structures arise in many biological and physical processes. Can you explain what do we mean by curved two-dimensional crystals?
All right. Now, okay, my theory, the theory I talked about, I should have said this, but I didn't, is strictly for a flat substrate. Remember, because of course, the substrate, if you're talking a two-dimensional system, if you produce your two-dimensional system, you usually have to put the system on something to support it. And this something you put it on is called a substrate, but unfortunately, the substrate is liable to have a huge effect on your system. Of course, if you take a small system, a bunch of atoms or something, then of course it will, liable to form something like a droplet of various sizes, and it's possible that interesting things can happen on the surface of this droplet, and then you will have a system, two-dimensional system in curved space. It's not too difficult to realize such a system, but it's not that easy either.
Okay, sir. Okay, thank you very much, sir. So I request Professor Anurag Sharma. Yeah.
So that was fascinating, sir. Professor Kosterlitz, your personal life along with physics, or in physics also you had many phases, high energy physics, and then coming to condensed matter theory and so on.
I did say it was a random walk.
Random walk, yeah, that's why. So what I would say is that you had love for accident prone sport, but you got accidented in the career, by accident to reach somewhere which ultimately took you to the heights, the rock climbing, the heights of science or physics, really. So it's a really fascinating story, and I'm sure the young students have and other researchers have got a lot of inspiration from you, how keep doing things, keep love for other things also along with your subject, and that will also give you some clues how to go through the random walk. So really, thank you very much. It was a great talk. Thank you very much.
Thank you very much, sir. And I would like to thank all the attendees as well as my fellow panelists for being there with us and attending this special public lecture by Professor Michael itself. Thank you very much, sir.
You're welcome.
So I seek your permission to close the session also. Fine. Sure. Thank you.
Bye-bye.
Thank you very much.
Yeah.